To help us understand this phenomenon, we'll take the help of an old friend, probability theory. It gives us a formal mechanism to capture uncertainty in the real world and lets us make sensible decisions even when we are not fully sure about something.
Since the assignment of cars and goats is random, it doesn't really matter which one we pick first. The chances that the car is behind one of these doors is the same as the chances that it's behind either of the other two.
We represent this by saying that the probability of the car being behind door A, which we denote by P of car A, is equal to P of car B, and that is equal to P of car C. Also, we know that one of these doors surely has the car behind it, and by convention the probability of something that is certainly true is set equal to 1. Therefore, we can say that the sum of these probabilities equals 1.
From these two statements, we can conclude that each of these doors has a 1/3 probability of the car being behind it. This is known as prior probability, which is essentially our best guess given no further evidence. Now let's say we now pick door A as our first choice.
Monty then opens one of the other two doors, say B, to reveal a goat, which clearly implies that door B does not have the car. Here, open B is an observation we just made, and the expression P of car B given open B is known as the posterior probability, that is, our belief after incorporating an observation, and in this case it is 0. Now, one way to think about this is that we have two doors left undisclosed, so the probability of the car being behind either one of them should be equal to half, right?
Wrong. You glossed over the fact that Monty knowingly opened a door with a goat behind it. He would never reveal the car at this stage.
Aha! So we are actually interested in finding out the posterior probability of the car being behind door C given Monty opened door B and the implicit rule that he would never reveal the car.
Correct. We can now express this posterior probability in terms of other quantities that we can compute using Bayes' theorem. Here, the first term, P of open B given car C, known as the likelihood, must be 1, because if the car is behind door C, Monty's only option is to open B, since we already picked A. The second term, P of car C, is simply the prior, which we already computed to be 1/3.
And the last term, known as marginal probability, is a little tricky to compute. There are three possibilities we have to consider. The car could be behind door A, which happens 1/3 of the time, and in this case Monty could open either of B or C with equal probability. Therefore, P of open B given car A would be half. Note that Monty cannot open door A as we've picked it as our first choice. Or, the car could be behind door B, which also happens 1/3 of the time, but in this case Monty will certainly not reveal it. Therefore, P of open B given car B is 0. Finally, the car could be behind door C, also 1/3 of the time, in which case Monty is forced to open door B. Hence, P of open B given car C is 1.
Let's plug these values back into our Bayes' rule formulation. As we can see, the probability that it is behind the other closed door has increased to 2/3. And even empirical evaluation indicates that a consistent switch strategy wins 2/3 of the time.
It is fascinating how a careful characterization of a given situation combined with a formal method can help us make decisions even in the face of uncertainty.